Okay, so now I want to talk briefly about the idea of overfitting. So before we do that, we have to think about what we mean by or notice that some learning rules are more flexible or complex than others. So that's the first idea to get into your head. So remember that a learning rule is, or in a supervised learning procedure, is a mapping from a training data set to a decision rule or a classification rule. So think of a learning rule that way. You give me a training set and I'm going to give you a classification procedure based on that training set using my learning rule. So some learning rules or learning procedures are more complex or flexible than others. So a really simple example is if I build a regression model with one predictor versus with 15 predictors versus with 150 predictors, the one with 150 predictors is naturally more flexible, more complex than the one with just one predictor. Maybe a less obvious example is in the nearest neighbor, k-nearest neighbor classifier, where in some sense, the one nearest neighbor rule is kind of more flexible or has more degrees of freedom than the 15 nearest neighbor rule. And we'll see that, well, I guess if we actually can just look at this picture from the elements of statistical learning. We've seen this before, and this is the 15 nearest neighbor decision boundary, whereas this is the one nearest neighbor decision boundary. So you can see like the decision boundary is a lot more complex in some sense, and that's the sense in which the one nearest neighbor classifier is kind of has more degrees of freedom, if you like, or more effective degrees of freedom. So actually, there are ways to formalize these ideas. So VC dimension is a general approach. If you're interested in those, you could look that up. We're not going to cover it for reasons of time, but you can basically quantify the notion of complexity or flexibility. In the parametric cases, it usually corresponds to something like the number of parameters. So if you're just getting your head around it, thinking about it in terms of a regression and thinking about it in terms of a regression model with 5 predictors versus 50 predictors might be a good starting point. Okay, so that's the idea that some decision rules or learning procedures, I should say, some learning procedures are kind of more flexible and more complex than others. So what's overfitting? So overfitting is the phenomenon by which, as the flexibility of a learning rule increases, so if you use a learning rule that's increasingly flexible, which might sound like a good thing, eventually its performance on data that it hasn't seen before, that is its test error. So if you think about data it's never seen before as its test error, sometimes called its generalization error or holdout error. Holdout refers to data that you've held out and not given to the learner, the procedure. So also called out of sample error. So all these test errors eventually start to increase, even though as you make fit a more and more complex model, the fit to the training data typically improves. So one way of thinking about this is that if you have too many degrees of freedom, too complex a model, too flexible a model, it starts to fit the noise instead of fitting the signal. So you can kind of see here that maybe that's what's going on, right? That the one nearest neighbor classifier, in classifying this blue point, the decision boundary here correctly classifies the blue point as blue, but that's because it saw that point. It's kind of very attuned to that training data. If that point had not been in the training data, then the decision boundary would not have included this little circle here surrounding it. So you can think of, adding these circles would probably actually hurt performance on future observations, because there will often be, actually points in this space are more likely to be orange than blue in the future. So classifying things in that area of the space as blue is actually a bad idea. Whereas the 15 nearest neighbor classifier doesn't do that. So you can see how a more flexible model can lead to worse performance on out of sample prediction, even though in sample, that is on the training data, the one nearest neighbor on the training data actually classifies every point exactly correctly, because it's its own nearest neighbor. So its performance on the training data is perfect, but its performance on test data would be worse. This is kind of a another picture illustrating this idea. So on the x-axis here, it's it's just a conceptual picture illustrating the idea that as a model goes from low complexity to high complexity, the prediction error on the training sample goes down. That's this blue line. But initially, maybe more complex, more flexible models are better on the test data as well. But there's kind of a sweet spot, and then as you make the model too flexible, too complex, you start to actually get worse, what's called generalization performance. Okay, so this is a phenomenon that we're going to talk about in more detail. So here's an example in the polynomial regression here. I'm going to follow that link just to show you here. So it's got some, I like this because it has code with it, so you can kind of replicate this. But basically the idea here is that they've just used linear regression to fit polynomials of increasing degree to these data. So sorry about the adverts. So the least flexible line, the simplest model, is this linear line here, the red one, and that's the degree 1 polynomial. And then this line here is the next simplest, so it's a degree 3 polynomial, and you can see it's kind of smooth. But then it fits polynomials of increasing degree, and you can see that the purple line here, or magenta line, which is the degree 20, it's pretty much, I mean, it's not quite joining up the training data points, but you can see here it's kind of trying its best to get as near to these data points as it can. And you could imagine that if you increase this degree further, you would eventually get a line that just joined up all the or fit that joined up the data points. I guess some of them are actually in exactly the same point on the x-axis, so it wouldn't be able to quite accomplish that. Maybe that's why it doesn't. In any case, so what you can see here is that probably the magenta line would not perform as well in future predictions as, say, this greenish line, the degree 3, for example, because it's fitting the noise and not the signal. Whether the degree 3 would do better than the simple linear rule, well, that's an interesting question. And actually, one way one might try and decide between models of different complexity, and one way people do use to decide between models of different complexity, is cross-validation. So, and that's part of your homework this week, to choose between, to try and select between different models or different approaches by cross-validation. Okay, so that's the idea of complexity, flexibility of a learning rule, and the notion of overfitting. And we'll come back in a minute and talk about ways to adapt learning rules to avoid overfitting when we talk about regularization.